Morning. Today we'll discuss about the least error squared technique, which is widely employed for signal analysis in numerical English. In the last lecture, we have seen the sampling theorem. We have gone through the statement of the sampling theorem, and we have also discussed the proof of Shannon's sampling theorem. And it states that the sampling frequency must be greater than or equal to twice of the maximum frequency which is to be analyzed. Let us suppose if you do have a signal which has a fundamental frequency of 50 Hz and it has second order harmonic, third order harmonic and fourth order harmonic and seventh order harmonic. Let us suppose your signal is having these many number of harmonics. Then if you sample the signal at twice, let us suppose if you sample the signal at 300 Hz, then you will be able to analyze the signal up to this level of harmonics. So these harmonics you may not be able to identify and analyze. So if you want to analyze your signal with all the harmonics included, then the maximum frequency, whatever which you do have, your sampling frequency must be greater than 350, twice of 350, which means it must be greater than 700 Hz. So this is what we have gone through in our last lecture, and we have also seen the correlation with a reference wave. So based upon the reference wave, these signals will be mathematically expressed. In Fourier analysis, we take sinusoidal and cosinusoidal signals. In Walsh analysis, we do take rectangular pulses. And Walsh analysis is not extensively employed now. In olden days, we used it to have difficulty with float problems, with float variables or float data. So nowadays, with the advent of modern computers, we are not employing Walsh analysis. We are usually employing Fourier analysis, but still in some applications where the waves will be, reference waves will be closer to your rectangular pulses, then we still are employing Walsh analysis. The other one is a wavelet analysis, which is finding its important significance in power systems in recent days, because in Fourier analysis we don't get any information about the time of occurrence of harmonic waves. That problem is solved in wavelet analysis. So that's fine. In fault analysis of power systems, we are extensively employing wavelet analysis nowadays. So many techniques have been discovered, they have been proposed in wavelet analysis nowadays. We can go through them in the literature. And we have compared all this analysis, all these techniques in the last lecture. In this lecture, now we will go through the least error squared technique. I hope that by the end of this lecture, you will be able to apply the least error squared technique for determining the harmonics in given sample data. So I'll start with the introduction to least error squared technique, and we will see the equations which are involved in that one, and then we will try to solve the problem on least error squared technique. So coming to the introduction of this particular method, we have already seen Fourier analysis type of representation, and we have also gone through Walsh analysis in our unit number 2. And this method is very similar to your Fourier analysis itself. It is also an advancement of your Fourier series. In this technique, it reduces the mean square error between the assumed and original signals. So let us suppose if you assume some sort of waveform, and let us suppose you do have some waveform, and this is your approximated wave. So slowly what happens is the error between them, let us suppose if this is the error, so the square of the error will be reduced in stepwise mechanism in this particular method. So here it is based on a Fourier series. So any signal whatever which you do have, it is represented just like your Fourier series. It will be represented as a DC component and a fundamental component and higher order. It can be up to infinity also. So your signal is represented as a summation of different frequency components. In numerical LS, particularly, this LES technique is widely employed, particularly to determine the higher order harmonics and also this DC component. Then, what is the major significance when compared to your Fourier series and least error square technique? The biggest difference between these two mechanisms is that, see, this is your mathematical expression. As already I told you, this is your signal, this is your DC components, and this is your fundamental components, right? This is your, let us suppose I am assuming that my even harmonics are, but before going for this, let me state you the difference between Fourier series, conventional Fourier series, and least error square method. In most of the times when you do represent this signal as a summation of different frequency components, in Fourier series we do stick that this is a DC component. But whereas in least error square technique we do have the advantage that we can use here a decaying component also can be introduced here as an approximation. Because in power systems what happens is we don't get any waveform, we don't get any direct DC component, a standard DC component. What happens is that your waveform, so let us suppose this is after your low pass filter. Let us suppose this is your signal. So this is your DC component, this is your fundamental component, this is your third harmonic component, and higher order of frequencies have been eliminated using your filtering techniques. Now, in power systems, we don't get this constant DC component here. Most of the times what happens is, it will be in form of decay. So which means that you don't get any particular pure or constant value of DC as an offset. This will be varying with respect to time. Even the DC component also will be varying with respect to time, and most of the times it will be decaying in nature. Your Fourier series doesn't take the approximation of decaying components, whereas that problem is eradicated in this least error square technique. Particularly in case of transients, when your signal is decaying, the DC component might be decaying most of the times. In that case, to get a perfect value of the perfect representation of the signal, least error square technique uses better results when compared to the conventional Fourier series. Okay, so I hope that now you have now understood the major difference between conventional Fourier series and the least error square technique. The biggest difference is that the DC component you can implement it in decaying format also. But in your UG level, I am omitting that particular concept. So I am directly going on with this mechanism, how this is being applied in power systems. See, let us suppose I am considering a signal now, I of t, which is having some DC component. So here at the UG level, I am just only considering the basic DC component, but in practice you can go with this one. Okay, you can use a decaying component also. Say I am assuming that there are no even harmonics present in my system. The higher order harmonics have been filtered out. So I am assuming that I do have only a constant DC component, a fundamental component, a third harmonic component, and a fifth harmonic component. So these indicate the frequencies, whereas these indicate the angles. Okay, so I can represent it as okay. So if this is the case, when I do expand this particular term, so this is your cos, if I take it as cos A plus B, I can expand this term, right? It is cos A cos B minus right. So based upon this, what I can do is that, see, I have expanded this entire term of I of t, the DC component remains the same, whereas the higher order, the fundamental component, the third harmonic component, and fifth order harmonic. These have been expanded. Now what I will do is nothing but I will try to separate this one. See, my entire time I am just now representing it in terms of my samples. So your entire signal of t is now divided into n number of intervals. Okay, this is 0, 1, 2, 3, 4, 5, 6, like that up to n. So my total time is nothing but n into the sampling time between these two. Okay, whereas this ts sampling time is 1 by my sampling frequency. This is sampling time, this is sampling frequency. If I substitute these things in the earlier equations, so wherever I get t, that will be replaced by this nts. Okay, so now this is my expression. Now if I write it in terms of my, see, this is my I. So if I keep n is equal to 1, so this expression will become, this will become 1. If I take at the second sample, at the first sample, I'll take n is equal to 1. At the second sample, I'll take n is equal to 2. Like that, n is equal to, you can take any number of samples to analyze this. Okay. See here, I have taken, see, I have taken here in this particular case, I have taken, so you can vary from n, varies from n to p. I can go up to p. Okay. See, this is for first one. I have taken these things do not vary, only, see, these components, they are not varying every time. So I am taking these things as constants. What is varying? Only these sine and cosine components are varying. So that's why I am representing it in this format. Okay. So if you want to take p samples, then these terms, they remain constant. Which harmonic components you want to take, that you need to take here. See, this matrix can be represented as A into x is equal to 2. The more the number of samples you do have, then the better will be your equation. See, this order is not going to vary. This is a number of harmonics. See, in this particular signal, I am considering DC, fundamental components, third harmonic, and fifth harmonic. So for DC, I'll get 1. For these things, I'll get 1 sine and 1 cos, 1 sine and 1 cos, and 1 sine and 1 cos. So totally 7. So this order will be 7 by 1. Whereas this order is nothing but here p by 7, where p is the number of samples which are considered. So the order is, this is p by 1, A matrix, sorry, p by 7. This is 7 by 1. And finally, this is p by 1. These are the samples, p number of samples which you want to take. The minimum number of samples which you need to take is nothing but 7 samples you are supposed to take. Minimum samples you need to take. Okay. So in the above equation, if you carefully see, there are 7 unknowns. So that's why what I have taken is 7. But let us suppose if you want to consider H harmonics. So for each of the harmonics, you will be getting 2. One is sine term, the other one is a cos term, and there will be a defaultly a DC term. So total, how many elements you need to find out? 2H plus 1. So that's fine. The size of A matrix will be P by 2H plus 1, where H is the number of harmonics which you need to identify. And P is your samples which you need to consider. And this is 2H plus 1 into 1. And size of B matrix will be P by 1. Okay. And do remember, the number of samples, how many samples you need to take. It must be minimum this 2H plus 1. The more the number of samples you take, the better it will be your data. You will get more accurate results. Okay. So in actual practice, what happens is that, as already I said, see, I need ultimately this one, right? So in this case, what you can write it as, this is A inverse B. But if you carefully see, A matrix is not a square matrix, and it is difficult for us to determine the inverse. If you take number of samples as 7, then it will be okay for you. But in actual practice, it is very difficult to determine but as already I said, more number of samples give you accurate results. So if you take 20 samples, then it will be good. But you see the order of matrix, it is equal to 20 by 1 now. Sorry, 20 by 7. which is tough call for you to take an inverse. So in that case, we generally follow pseudo inverse. See, in actual practice, what happens is the sample values of any signal, they might be having observational errors. So in that case, the considered equations are more than the 2x plus 1. Because of this, A matrix becomes non-square inverse, non-square matrix. And for such non-square matrix, inverse is obtained using this particular formula. Try to remember this one, where A is your matrix. So this is your pseudo inverse. Okay. So now your matrix, whatever the matrix which you do have now, instead of this one, what you will write? Pseudo inverse into B. The pseudo inverse formula is this one. A transpose into A whole inverse. So now let us suppose if you do have 20 samples and you do have 7 harmonics. So this particular one, this is 20 by 7 transpose, so you will get 7 by 20 into 20 by 7. So what you will get here? You will get 7 by 7. So 7 by 7 inverse is again 7 by 7 into, this is again A transpose, it is 7 by 20. Okay. So in this way you can, so what you will get? You will get 7 by 20. Right. So in this way you can get the things which you want. And next is a numerical problem on this particular. So I'll close this lecture now. So I hope that you have now understood. You can take so many number of samples to get accurate results, but since we do have difficulty in finding the inverse, the best way is nothing but you can use the pseudo inverse technique for determining the inverse of that particular matrix, and you can get the magnitude of the harmonics along with the phase angles. Okay, so with this